The manufacturing landscape of the 21st century is increasingly defined not by the brute force of traditional industrial chemistry, but by the microscopic, hyperspecific precision of biological catalysts known as enzymes. For generations, the production and refinement of consumer goods relied heavily on harsh chemical interventions, extreme temperatures, and intense mechanical processing. While these traditional methods yielded functional products, they frequently resulted in the degradation of the raw materials, inefficiency in manufacturing throughput, and inconsistent product quality. The integration of industrial enzymes into everyday manufacturing processes represents a profound technological leap, moving the locus of control from the macro-industrial scale to the precise molecular level. Enzymes are complex, three-dimensional proteins produced by all living organisms to facilitate and accelerate biochemical reactions. Their fundamental utility lies in their role as catalysts. They dramatically lower the activation energy required for a specific chemical reaction to occur, thereby increasing the rate of that reaction without being consumed or permanently altered in the process. The defining characteristic that makes enzymes so exceptionally valuable to industrial manufacturing is their extraordinary substrate specificity. Unlike a harsh acid or a caustic alkaline solution, which will indiscriminately attack and break down any vulnerable chemical bond it encounters, an enzyme is engineered by nature to interact with only one specific type of molecule, known as its substrate. This interaction is frequently conceptualized through the lock and key model, or more accurately, the induced fit model. The surface of the enzyme features a highly specialized pocket known as the active site. The three-dimensional shape, charge distribution, and hydrophobic or hydrophilic nature of this active site correspond perfectly to the target substrate. When the substrate enters the active site, the enzyme subtly alters its own shape to bind the molecule tightly, placing physical and electrical stress on specific chemical bonds within the substrate. This targeted stress facilitates the chemical reaction, often the cleavage of a complex polymer into smaller, more manageable fragments with unparalleled efficiency. Once the reaction is complete, the resulting products are released, and the enzyme immediately resets, ready to catalyze the same reaction on a new substrate molecule thousands of times per second. The industrial application of these biological catalysts has evolved from early rudimentary experiments into a highly sophisticated multi-billion-dollar scientific discipline. Modern biochemical engineering allows for the manipulation of molecular structures to achieve optimal product performance, maximize manufacturing yields, and drastically enhance consumer satisfaction across a vast array of goods. By integrating specific enzymes into their manufacturing and product formulations, industries can completely bypass the need for harsh chemical treatments, achieving unprecedented levels of refinement and engineering goods with highly specialized market-driven functionalities. This comprehensive analysis provides an exhaustive examination of how specific classes of industrial enzymes are synthesized, stabilized, and deployed to enhance high-performance detergents, food and beverage engineering, and textile and cosmetic manufacturing, detailing the profound biochemical mechanisms that operate entirely unseen by the average consumer. High-performance detergents, molecular cleaning agents. The formulation of modern laundry and automatic dishwashing detergents represents one of the most complex and technologically advanced applications of commercial enzymology. The everyday stains and soils encountered by consumers are rarely simple, easily dissolved chemical compounds. Rather, they are complex polymeric biological matrices, mixtures of tightly bound proteins, hydrophobic lipids, and resilient carbohydrates that adhere strongly to the microscopic crevices of textile fibers and the solid surfaces of dishware. Historically, the removal of these stubborn soils relied heavily on intense mechanical agitation, boiling water temperatures, and aggressive, highly alkaline soaps to physically dislodge and break apart the materials. However, the introduction of specialized hydrolytic enzymes has fundamentally transformed the mechanics of cleaning, allowing modern detergents to deconstruct complex soils systematically at the molecular level, far surpassing the traditional capabilities of soap and water. These detergent enzymes operate entirely through the process of hydrolysis, a chemical reaction in which the active site of the enzyme utilizes a water molecule to cleave robust chemical bonds, thereby fracturing large, insoluble stain polymers into much smaller, highly water-soluble fragments that are effortlessly lifted and rinsed away by the wash liquor. Proteases or proteolytic enzymes form the absolute cornerstone of any high-performance enzymatic detergent formulation. The history of utilizing enzymes in laundry applications dates back to 1913, when Otto Röhm patented the use of trypsin, a proteolytic enzyme extracted from the pancreases of slaughtered pigs, in a German detergent brand named Bernus. However, because trypsin exhibited poor stability in the alkaline environment of laundry water and degraded rapidly, the concept failed to gain widespread commercial traction. The true breakthrough occurred in the 1960s with the launch of Alkylase, a highly robust bacterial protease derived from Bacillus species that demonstrated exceptional stability and performance in the presence of alkaline builders and synthetic surfactants. Today, proteases are universally deployed to target and dismantle protein-based stains, which are notoriously difficult to remove because proteins tend to denature, coagulate, and bind firmly to fabric fibers when they dry or are exposed to the heat of a washing machine. Common household protein stains include human blood, sweat, bodily fluids, egg yolk, dairy products, grass, and various meat residues. At the molecular level, a protein is a massive macromolecule consisting of long, intricate chains of amino acids held together by incredibly strong covalent linkages known as peptide bonds. When a proteinaceous stain like blood dries on a cotton shirt, these massive protein chains form a rigid, highly insoluble crust that physical scrubbing alone cannot easily break. Proteases function as highly selective molecular scissors engineered to dismantle this crust. When a protease molecule floating in the wash water encounters the protein stain, its active site identifies the specific sequence of amino acids and locks on to the peptide bond. The enzyme then manipulates the electron distribution around the bond, rendering it highly susceptible to a nucleophilic attack by a water molecule. This perfectly catalyzed hydrolysis reaction neatly severs the long, insoluble protein chain into much shorter segments known as peptides, and eventually into individual amino acids. Because these smaller, fragmented molecules possess significantly lower molecular weights and a higher degree of electrical polarity, their solubility in the aqueous wash water increases exponentially. Once dissolved, the surfactant components of the detergent easily encapsulate these protein fragments within protective micelles, suspending them in the liquid and preventing them from redepositing onto the clean fabric during the rinse cycle. Furthermore, the engineering of modern proteases has advanced to the point where scientists utilize directed evolution and site-directed mutagenesis to create highly specialized variants that exhibit peak catalytic efficiency across diverse temperature spectrums, ensuring that rapid protein degradation occurs effectively even in unheated cold water wash cycles, optimizing overall cleaning performance. In the realm of automatic dishwashing, where there is no physical scrubbing action, specialized proteases are strictly required to remove baked-on egg and meat films. Modern dishwashing proteases have even been specifically engineered to overcome and bypass the high levels of natural protease inhibitors inherently present in egg whites, which would otherwise neutralize the detergent's effectiveness and leave dishes coated in a hazy protein film. The lipolytic breakdown of fats and oils. While proteases are exceptionally effective at dismantling proteins, they are completely useless against hydrophobic, lipid-based stains such as cooking oils, butter, lard, salad dressings, cosmetics, and human sebum. Lipids present a profound chemical challenge to traditional aqueous washing systems because their fundamental molecular structure is nonpolar, meaning they aggressively repel water. This hydrophobicity makes it incredibly difficult for standard detergent surfactants to penetrate, surround, and emulsify the stain completely. To combat these recalcitrant fatty soils, detergent chemists incorporate lipases, a class of enzymes specifically designed to interface with and dismantle lipid molecules. The primary constituents of animal fats and vegetable oils are triglycerides. A triglyceride molecule consists of a central glycerol backbone attached to 3 long-chain fatty acids via ester bonds. When a lipase enzyme encounters a fat stain, it faces a unique challenge of operating at the lipid-water interface, as the enzyme itself is dissolved in the water while the substrate is an insoluble oil droplet. Upon absorbing to this hydrophobic interface, the lipase undergoes a fascinating structural shift, often referred to as interfacial activation, which opens a protective lid on the enzyme and exposes its active catalytic site directly to the lipid substrate. The lipase then systematically proceeds to hydrolyze the ester bonds, chemically severing the long, water-repelling fatty acid chains from the central glycerol backbone. This enzymatic cleavage transforms the bulky, utterly water-insoluble triglyceride into a mixture of diglycerides, monoglycerides, free fatty acids, and free glycerol. These resulting fragmented compounds are significantly more hydrophilic, or water-loving, than the original intact triglyceride. Consequently, the fragmented lipid molecules can interact readily with the surrounding wash water and the detergent surfactant micelles, allowing the once stubborn grease stain to be easily lifted from the microscopic textile fibers and dispersed evenly into the wash liquor. The inclusion of lipases is particularly critical for maintaining the long-term appearance and olfactory quality of garments. Without lipases, the incomplete removal of lipids during a wash cycle leads to a gradual, invisible accumulation of organic fatty matter within the fabric structure. Over time, these residual lipids oxidize and go rancid, resulting in the severe yellowing of white fabrics and the development of deep-seated, stale odors that are impossible to mask with perfumes. Furthermore, advanced lipases utilized in modern powder detergents have even been specifically engineered to resist oxidative degradation, ensuring they remain highly active even in the presence of the aggressive bleaching agents commonly used in heavy-duty formulations. Amylase-driven hydrolysis of complex carbohydrates. Carbohydrate-based soils, particularly starches derived from foods such as pasta, potatoes, rice, gravies, oatmeal, and infant formula, present an entirely different but equally formidable challenge in laundering and automatic dishwashing. Starch is a massive high molecular weight polysaccharide composed of thousands of repeating glucose units linked together by specific alpha 1.4 glycosidic bonds. When a starchy food residue dries on a fabric surface or a dinner plate, it forms a rigid, highly adhesive polymeric film. This film not only acts as a stubborn stain in its own right, but also behaves exactly like a biological glue, binding other particulate soils, dirt, and pigments to the fabric or dishware, effectively cementing the grime in place. To combat these intricate, glue-like carbohydrate networks, detergent manufacturers deploy amylases, specifically alpha amylases. Alpha amylases act as endoenzymes, meaning their active sites are designed to randomly cleave the internal alpha 1.4 glycosidic bonds deep within the massive starch polymer, rather than solely attacking the terminal ends of the chain. By rapidly and relentlessly snipping the long amylose and highly branched amylopectin molecules into much shorter, highly soluble segments known as dextrins, maltose, and eventually individual glucose molecules, the amylase completely destroys the structural integrity of the starch film. This rapid enzymatic depolymerization not only removes the primary carbohydrate stain, but also completely dissolves the biological glue, liberating any secondary dirt or particulate soils that were trapped within the starchy matrix, allowing the surfactants to wash everything away cleanly. In the realm of automatic dishwashing, amylases are arguably the most critical enzymatic component. While the high-pressure water jets inside a dishwasher are capable of physically knocking off large chunks of food, They frequently leave behind thin, stubborn films of baked-on or caked-on starch that build up into a dull, opaque layer over multiple wash cycles. Amylases relentlessly digest these thin films, ensuring that glassware and plates emerge sparkling and completely free of residual carbohydrate haze. To accommodate the extreme conditions of modern washing environments, industrial alpha amylases have been aggressively engineered for high pH stability, allowing them to function at peak efficiency in the highly alkaline solutions common to automatic dishwashing detergents, ranging from pH 6 to 11. Advanced targeted solutions, Mannanases, Pectate Lyases, and Cellulases. As global consumer diets have shifted and the food processing industry has evolved to include a wider array of complex thickeners and stabilizers, detergent manufacturers have been forced to expand their enzymatic arsenals to address these new, highly specific stains. Just after the turn of the century, two entirely new classes of highly specialized enzymes entered the commercial detergent market: Mannanases and Pectate Lyases. Mannanases are precisely engineered to target and break down mannans, which are complex oligosaccharides and polysaccharides, heavily utilized as thickeners, texturizers, and stabilizers in a vast array of modern processed foods. Guar gum and locust bean gum, common mannan-based additives, are found abundantly in products such as commercial ice cream, barbecue sauce, salad dressings, mayonnaise, milkshakes, chocolate syrups, and even certain cosmetics and toothpastes. These thickeners are designed to be highly viscous and sticky, properties that unfortunately make them incredibly difficult to wash out of fabrics. Mannanases solve this problem by selectively hydrolyzing the specific chemical linkages within the mannan polymers, breaking the thick, gummy residue down into simple, highly soluble sugars that instantly wash away in the rinse water. Similarly, Pectate Lyases and pectinases are deployed to specifically target pectin, a complex gel-forming structural carbohydrate found naturally in the primary cell walls of terrestrial plants and fruits. Consequently, Pectate Lyases are highly effective and strictly necessary for dismantling stains originating from fresh fruit juices, tomato pastes, marmalades, jams, and vegetable-based baby foods. By cleaving these specific plant-based polysaccharide structures, both Mannanases and Pectate Lyases prevent these viscous food residues from acting as an adhesive base that could attract and bind other ambient soils from the washwater onto the fabric. Cellulases, conversely, serve a fundamentally different and highly innovative purpose within laundry formulations. Rather than targeting exogenous food or bodily stains, cellulases are designed to interact directly with the cellulose fibers of the cotton fabrics themselves. Over time, the repeated physical friction of wearing garments, combined with the aggressive tumbling action of the washing machine, causes the microscopic cotton fibers to fray and splinter. This mechanical damage creates tiny, fuzzy surface protrusions known as microfibrils. These microfibrils act like microscopic nets, trapping passing particulate soils from the washwater, such as clay, soot, and rust, leading to a phenomenon known as redeposition, which gives older clothes a chronically dull, gray, and dingy appearance. Furthermore, these tangled microfibrils clump together to form highly visible pills on the garment's surface, severely degrading its texture and making the fabric look aged and worn. Cellulases address this by acting specifically on these damaged, protruding fibers. The enzyme hydrolyzes the cellulose exactly at the base of the surface layer, cleanly severing the frayed microfibrils from the main body of the yarn. This targeted enzymatic shaving action, often referred to as biopolishing during the wash cycle, restores the fabric's original smooth surface, prevents the entrapment of particulate dirt, drastically enhances color brightness by allowing light to reflect uniformly off the smooth yarn, and maintains the garment's original soft, luxurious texture over a vastly extended lifespan. Food and beverage engineering. precision modification and structural control. While detergents use enzymes for total destruction and removal, the food and beverage industry relies on enzymes to achieve exact, highly controlled biochemical transformations. These targeted modifications are designed to optimize product texture, dramatically extend shelf life, enhance visual clarity, and alter nutritional profiles to meet specific consumer dietary needs. Unlike harsh chemical processing, which involves extreme heat or aggressive acids that inevitably degrade sensitive volatile flavor compounds, destroy essential vitamins, and alter the fundamental nutritional architecture of the food, enzymatic intervention offers unparalleled precision. Because enzymes exhibit stereospecificity and bond specificity, they allow food manufacturers to isolate and modify a single specific component within an incredibly complex food matrix, while leaving the surrounding structural proteins, fats, and essential nutrients entirely untouched and perfectly preserved. The production of lactose-free dairy products serves as a paramount example of utilizing industrial enzymes to tailor the nutritional profile of a food product for a specific physiological requirement, unlocking dairy consumption for a massive segment of the global population. Lactose is a naturally occurring, highly concentrated disaccharide sugar present in all mammalian milk. Structurally, lactose is composed of two simpler monosaccharide molecules, glucose and galactose, bound together by a beta-1,4-glycosidic linkage. The normal human digestion of lactose strictly requires the presence of lactase, an endogenous digestive enzyme produced by the cells lining the small intestine. However, an estimated 70% of the global adult population, particularly those of Asian, African, and certain European descents, exhibit a natural genetic downregulation of lactase production following weaning, a physiological condition universally known as lactose intolerance. In the absence of sufficient endogenous lactase, the intact bulky lactose molecules cannot be absorbed through the intestinal wall into the bloodstream. Instead, they pass unabsorbed into the large intestine, where they serve as a highly fermentable food source for the resident colonic bacteria. This massive bacterial fermentation results in the rapid production of vast quantities of gas, while the presence of the unabsorbed sugars draws excess fluid into the intestinal tract via osmosis, leading directly to the severe bloating, abdominal cramps, and urgent diarrhea that characterize the intolerance. To engineer high-quality dairy products that completely bypass this digestive hurdle, dairy manufacturers employ exogenous lactase, formerly known in biochemistry as beta-galactosidase. The lactase enzymes used commercially are typically derived from the carefully controlled fermentation of specific microbial sources, such as highly selected strains of mold or yeast that possess generally recognized as safe GRAS status from regulatory bodies like the US FDA. The industrial processing of lactose-free milk generally follows two primary methodologies: the batch pre-hydrolysis process and the continuous aseptic process. In the highly common batch process, a precisely calculated dosage of neutral liquid lactase is introduced directly into a vast industrial holding tank filled with raw or gently thermonized milk. Because the milk at this stage is not yet fully sterilized, it must be maintained at significantly lowered temperatures, typically hovering between 4 and 8 degrees Celsius, to completely suppress the proliferation of unwanted ambient bacteria or spoilage organisms. Over a prolonged incubation period, usually lasting up to 24 hours under continuous slow agitation to prevent the milk fat from creaming to the surface, the lactase enzymes systematically encountered the millions of dissolved lactose molecules. The enzymes bind to the disaccharides and actively hydrolyze the beta-1,4-glycosidic linkage, perfectly cleaving the lactose apart into its constituent glucose and galactose subunits. Once the enzymatic cleavage is complete and quality control testing confirms the absence of intact lactose, The resulting milk undergoes standard high-heat pasteurization or ultra-high temperature sterilization. This extreme heat treatment irreversibly denatures the lactase enzyme, completely destroying its delicate three-dimensional folding structure and permanently halting all catalytic activity. Consequently, the final packaged product sitting on the supermarket shelf contains no active residual enzyme. An interesting and highly beneficial chemical byproduct of this enzymatic process is a subtle but distinct alteration in the product's flavor profile. Because the liberated individual glucose and galactose molecules interact more readily with the sweet taste receptors on the human tongue, possessing a much higher relative sweetness index than the original bulky lactose molecule, lactose-free milk exhibits a distinct, naturally sweeter taste without the manufacturer having to add any extraneous sugars, syrups, or artificial sweeteners to the formulation. This technology, initially pioneered on an industrial scale in 1985 by the USDA Agricultural Research Service, has since exploded into a massive global industry, allowing companies like Valio, Lactalis, and Fairlife to produce entire lines of easily digestible milk, cheeses, ice creams, and specialized high-protein recovery shakes. Bakery science, delaying staling and enhancing dough architecture. The commercial baking industry utilizes an incredibly complex and highly synergistic consortium of enzymes to manipulate the precise rheological properties of raw dough, optimize gas retention during the critical fermentation phase, and drastically retard the staling process in the finished baked good, thereby ensuring a vastly extended commercial shelf life and preserving product quality. Bread staling, chemically defined as retrogradation, is a profound misconception among the general public. It is not simply the loss of moisture or the bread drying out. Rather, staling is a profound, inevitable structural metamorphosis of the starch molecules within the baked crumb. During the intense heat of the baking process in the oven, the densely packed starch granules present in the wheat flour absorb surrounding water and swell massively, a physical phenomenon known as gelatinization. As they swell and burst, the two primary components of the starch, the linear amylose chains and the massive, highly branched amylopectin molecules, leach out of the granules and form a chaotic, amorphous gel-like network that traps water and gives fresh, hot bread its incredibly soft, tender, and pliable texture. However, the moment the bread exits the oven and begins to cool, these highly energetic molecules immediately attempt to return to their original, lower-energy, highly ordered crystalline states. The linear amylose molecules crystallize very rapidly within the first few hours, which is actually desirable as it sets the initial structural integrity of the loaf. But it is the slow, relentless, continuous recrystallization of the outer branches of the massive amylopectin molecules over several days that is the true culprit of staling. As these outer branches slowly align and form rigid double helices, they squeeze out the trapped water and lock the entire crumb structure into a solid matrix, causing the bread to become progressively rigid, firm, harsh, and thoroughly stale. To combat this relentless structural hardening and extend shelf life by weeks, commercial bakers incorporate highly specialized anti-staling enzymes, primarily advanced bacterial alpha amylases and specifically maltogenic amylases. These specific enzymes become highly active during the baking process as the dough temperature rises. They act strategically, snipping and cleaving the long protruding outer branches of the amylopectin molecules into much shorter malto-oligosaccharides and low molecular weight dextrins before the heat of the oven completely denatures the enzymes. By significantly reducing the chain length of the amylopectin branches, the enzymes physically impede and sabotage the molecule's ability to realign and form the tightly bound double helices required for recrystallization. These enzymatically shortened chains act as structural roadblocks, interfering with the rigid continuity of the starch network and ensuring that the crumb remains remarkably soft, moist, tender and highly resilient for an extended duration. Recent advancements have even introduced specialized G4 amylases, which produce maltotetrose, a specific 4-sugar molecule that interferes with starch-gluten interactions even more efficiently than the maltose produced by older enzymes, resulting in an incredibly low staling rate and supreme softness. Beyond the amylases that manage the starch, Cellulases and Lipases play absolutely critical roles in managing the architecture of the raw dough before it ever reaches the oven. Wheat flour naturally contains non-starch polysaccharides known as arabinoxylans or pentosans. While making up only a small percentage of the flour, these massive molecules aggressively absorb and trap vast amounts of water, fiercely competing with the crucial gluten proteins for hydration. If the gluten cannot hydrate properly, the dough becomes stiff, brittle, and impossible to machine. Endoxylenases are added to specifically hydrolyze the backbone of these complex carbohydrates. This enzymatic cleavage rapidly breaks down the arabinoxylans, releasing the trapped water and redistributing it directly to the gluten network. This targeted enzymatic hydration significantly improves the extensibility, flexibility, and overall machinability of the dough, yielding a final loaf with a superior uniform volume and a perfectly structured crumb. Concurrently, lipases are aggressively utilized to manipulate the endogenous lipids naturally present within the wheat flour, allowing bakers to completely replace artificial chemical emulsifiers to achieve a clean label product. Wheat lipids are primarily non-polar triglycerides, which offer little structural benefit to the dough. Lipases hydrolyze these triglycerides, specifically cleaving off fatty acids to transform them into highly functional mono- and diglycerides, as well as lysolipids. These enzymatically generated compounds are highly amphiphilic, acting as incredibly powerful, entirely natural in situ emulsifiers. By radically altering the hydrophobicity of the lipid matrix within the dough, these emulsifiers migrate to and reinforce the delicate liquid films that surround the millions of microscopic carbon dioxide gas bubbles generated by the fermenting yeast. This profound structural reinforcement of the gas-cell interface prevents the bubbles from coalescing into massive irregular holes or rupturing prematurely under the mechanical stress of baking. The result is a bread with an incredibly fine, perfectly uniform crumb grain, maximized loaf volume, and a lighter, airier texture that feels exceptionally delicate on the palate. Furthermore, by breaking down the fats, lipases release naturally occurring pigments dissolved within the lipids, which are then easily oxidized by ambient air, resulting in a significantly brighter, whiter breadcrumb, without the need for harsh chemical bleaching agents. Clarification and extraction in the beverage industry. The aesthetic, textural, and operational qualities of commercial fruit juices and alcoholic beverages are deeply reliant on intensive enzymatic processing. When fruits such as apples, grapes, sweet limes, or watermelons are subjected to mechanical pressing to extract their liquid, the resulting raw juice is heavily burdened with suspended cellular particulate matter and dissolved complex carbohydrates. This results in a highly viscous, murky, and utterly opaque fluid that is entirely unappealing to the modern consumer and incredibly difficult to process further. The primary culprit behind this persistent gel-like cloudiness is pectin, a massive, highly complex, branched structural heteropolysaccharide that essentially acts as the biological cement holding plant cell walls together. In the extracted juice, these long, interwoven pectin molecules form a dense, sticky colloidal matrix that firmly traps microscopic cellular debris, proteins, and starches, preventing them from settling to the bottom by gravity and severely impeding any attempt at traditional mechanical filtration by instantly blinding the filter membranes. To achieve the brilliant, flawless clarity expected of premium commercial juices and fine wines, processors introduce a cocktail of pectinases. This class of enzymes includes specific actors such as alpha-pectin lyases, polygalacturinases, and pectinesterases, which work in a highly coordinated concert to systematically dismantle the massive pectin polymer. The enzymes rapidly depolymerize the long carbohydrate chains into much smaller, highly soluble galacturinates, which drastically reduce viscosity. Importantly, the degradation of the pectin removes the protective colloidal suspension that kept the larger particulates afloat. The destabilized cloud particles, which consist largely of proteins and polyphenols, rapidly aggregate together, forming much larger, heavier clusters in a process known as flocculation. This enzymatically induced flocculation allows the manufacturer to easily and rapidly separate the solid waste from the liquid via high-speed centrifugation or standard membrane filtration. The result is a perfectly transparent, highly stable juice with a significantly increased overall extraction yield, as the enzymes break down the fruit pulp more completely, liberating trapped liquid and resulting in a much more concentrated, vibrant flavor and color profile. Advanced optimization parameters utilizing response surface methodology allow manufacturers to precisely calculate the exact enzyme concentration, temperature, and incubation time required to achieve maximum juice recovery and perfect optical lightness while minimizing viscosity and turbidity. Similar, though distinct enzymatic interventions are foundational to the mass production of beer. The entire brewing mashing process is essentially an exercise in highly controlled enzymatic hydrolysis. Malted barley contains massive internal starch reserves that must be converted into simple fermentable sugars for the brewing yeast to consume and convert into alcohol. During the mash, the crushed grain is mixed with warm water, activating the endogenous amylase enzymes naturally present in the malt, or exogenous commercial amylases added by the brewer if adjunct grains like corn or rice are heavily used. The precise temperature at which the brewer holds the mash dictates exactly which specific enzyme dominates the conversion process, allowing them to custom engineer the final profile of the beer. Alpha amylase, which operates optimally at slightly higher temperatures, typically 145 degrees Fahrenheit to 158 degrees Fahrenheit, acts by rapidly chopping the massive insoluble starch molecules randomly in the middle of their chains. This action creates varied, larger, non-fermentable complex sugars known as dextrins. The yeast cannot consume these larger dextrins, so they remain in the final beer, contributing heavily to its final viscosity, rich mouthfeel, and full body. Conversely, beta amylase operates strictly lower temperatures, 131 degrees Fahrenheit to 149 degrees Fahrenheit. Beta amylase is highly methodical. It starts at the ends of the starch chains and meticulously cleaves off maltose, a highly fermentable 2-glucose sugar unit, one by one. If the brewer holds the mash in the lower temperature range, the highly active beta amylase will produce massive quantities of maltose, giving the yeast an abundant food source, which drives the ultimate alcohol content higher and results in a very dry, light-bodied beer. Additionally, exogenous beta-glucanases and xylanases are frequently supplemented to the mash to target beta-glucans and arabinoxylans, which are tough structural polysaccharides found densely packed in the grain cell walls. If left unbroken, particularly when brewing with high-protein grains like wheat, oats, or under-modified malt, these beta-glucans dissolve into the hot water and create a highly viscous, gummy, gelatinous mash. This thick sludge clogs the filtration equipment during the lautering phase, stalling the separation of the liquid wort from the spent grain husks and causing massive operational bottlenecks in the brewhouse. The addition of beta-glucanase enzymes rapidly slices through these structural polymers, drastically reducing the mash viscosity, ensuring a rapid, highly efficient lautering process, and guaranteeing a high brewhouse throughput with maximum extract recovery. Flavor modulation and the restructuring of animal proteins. Enzymes are also meticulously utilized to eliminate highly undesirable flavor compounds that are naturally present in raw agricultural materials, vastly improving the sensory profile of the final consumer product. In the citrus juice industry, processors constantly contend with extreme bitterness or delayed bitterness caused by the presence of complex molecular compounds such as naringin, limonin, and various tannins. Naringin is a flavonoid glycoside that is exceptionally abundant in grapefruits, quinoa, sweet oranges, and mandarins. To eradicate this harsh astringent profile without resorting to chemical masking agents or significantly altering the juice's inherent nutritional and antioxidant value, the highly specialized enzyme naringinase is deployed. Naringinase is a fascinating dual-action hydrolytic enzyme complex containing two distinct activities, alpha-L-rhamnosidase and beta-D-glucosidase, which are often located on two separate polypeptide chains within the complex. In a highly precise sequential two-step molecular mechanism, the alpha-L-rhamnosidase first attacks the naringin molecule, specifically cleaving off the rhamnose sugar moiety, converting the parent compound into an intermediate substance called prunin. Prunin is already substantially, about 33%, less bitter than the original naringin. Immediately following this first cut, the beta-D-glucosidase activity engages, severing the remaining glucose molecule and transforming the prunin into naringenin. Naringenin is entirely non-bitter, completely neutralizing the astringent taste profile of the juice. Similarly, specialized tannase enzymes, which belong to the superfamily of esterases, are utilized as biocatalysts to hydrolyze the complex ester bonds within tannic acids, liberating gallic acid and glucose, further refining the smooth sensory experience of fruit-based beverages and ensuring wide consumer acceptance. In the realm of protein processing, specifically within the dairy and meat industries, an entirely different class of enzyme has revolutionized product structuring, transglutaminase. Frequently referred to in colloquial terms as meat glue, transglutaminase is an enzyme predominantly produced via microbial fermentation of Streptomyces bacteria that acts as an unparalleled industrial biological adhesive. While the hydrolytic enzymes discussed previously are designed to break bonds apart, transglutaminase is designed to build them. Its specific biochemical function is to catalyze a distinct acyl transfer reaction, forging highly resilient permanent covalent bonds known as isopeptide bonds between two specific commonly occurring amino acids, the gamma carboxamide group of a glutamine residue and the epsilon amino group of a lysine residue. Because these two specific amino acids are naturally ubiquitous in almost all animal and plant proteins, transglutaminase can seamlessly and permanently cross-link disparate pieces of muscle tissue, plant-based proteins, or dairy casein into a single, highly cohesive, uniform matrix. In the dairy industry, transglutaminase is added during the fermentation of yogurt and the production of certain cheeses. By creating a vast, intertwined network of cross-linked casein proteins, the enzyme dramatically improves the firmness, consistency, and viscosity of the yogurt gel. It creates a significantly thicker, creamier mouthfeel, provides a luxurious, velvety sensation, and stabilizes the protein structure so perfectly that it completely prevents syneresis, the highly undesirable separation of watery whey that often pools at the top of yogurt containers, thereby significantly extending the premium quality and shelf life of the product. In the meat processing industry, the applications of transglutaminase are even more profound. The meat industry routinely generates massive quantities of low-value, irregularly shaped trimmings and offcuts during the butchering of cattle, pigs, and poultry. Historically, these pieces were ground into low-value sausage or hamburger meat. Transglutaminase allows processors to bind these smaller, high-quality but low-value trimmings together tightly, pressing them into molds to create uniform, high-value, restructured steaks, roasts, or bacon slabs. The biochemical cross-linking generated by the enzyme is exceptionally stable. Unlike gelatin or starch binders, the isopeptide bonds do not melt, degrade, or separate upon intense cooking heat, deep freezing, or high-speed physical slicing. Consequently, the restructured meat handles, cooks, and presents on the plate identically to an intact, whole muscle cut. Furthermore, transglutaminase dramatically improves the textural firmness and water-holding capacity of the restructured product, minimizing moisture loss during cooking and optimizing the geometry of the final goods for automated high-speed slicing and packaging systems, radically improving the economic yield and efficiency of the meat processing facility. Textile and cosmetic enhancements, precision surface biology. The application of industrial enzymes in the manufacturing of textiles and personal care products focuses primarily on the highly controlled modification of biological surfaces, such as natural woven fabric fibers and the outermost cellular layers of human skin. By leveraging the extreme selectivity and mild operating conditions of enzymes, manufacturers and formulators can achieve dramatic, highly desirable physical alterations, such as extreme softening, high-contrast color fading, and deep dermal exfoliation without inflicting the severe mechanical destruction, chemical burns, or structural degradation typically associated with traditional abrasive, acidic, or caustic techniques. The iconic faded, worn, and distressed appearance of denim jeans was historically achieved by a brutal brute force mechanical process universally known as stonewashing. During the height of the stone-washed craze in the 1970s and 1980s, raw denim garments were loaded into massive industrial-scale washing machines alongside substantial quantities of highly abrasive volcanic pumice stones. As the massive machines tumbled, the intense physical friction and pounding of the heavy stones literally tore away the outermost layers of the dyed cotton yarn, revealing the pristine white core beneath, and thereby removing the trapped indigo dye to create a faded look. While highly effective at producing the desired worn aesthetic, this primitive method was an operational nightmare. The aggressive pounding caused profound, irreversible damage to the tensile strength of the garment, frequently destroying hems, rapidly fraying seams, and severely shortening the wearable lifespan of the jeans. It severely degraded the expensive industrial washing machinery, leading to massive maintenance costs. Furthermore, the continuous grinding of the pumice generated massive, unmanageable quantities of abrasive pumice dust and thick, gritty sludge, which frequently clogged factory drainage passages, damaged the local environment, endangered employee respiratory health, and required highly intensive, tedious manual labor simply to brush the sandy stone fragments out of the pockets of the finished jeans before they could be sold. The introduction of specialized cellulase enzymes fundamentally overhauled the entire denim industry, completely replacing the destructive physical abrasion of rocks with precise microscopic biochemical hydrolysis in a revolutionary process appropriately termed biostoning or enzyme washing. Cotton denim is composed almost entirely of cellulose, a massive, long, linear polymer consisting of thousands of glucose molecules tightly bound together by strong beta-1,4-glycosidic linkages. When denim is dyed with indigo, the dye molecules do not penetrate deeply into the core of the cotton yarn. Rather, the blue chromophore sits trapped strictly within the microscopic spaces of the outermost surface fibers. Cellulases, originally derived for commercial use from robust fungi like Trichoderma and Humicula, are uniquely and perfectly capable of identifying and binding directly to these exposed cellulosic fibrils on the fabric surface. Once bound securely to the fiber, the cellulase enzyme catalyzes the rapid cleavage of the beta-1,4-glycosidic bonds, effectively chewing away and dissolving the absolute microscopic surface layer of the cellulose into smaller, harmless oligosaccharides and simple glucose sugars. As this very top layer of the cotton fiber dissolves completely into the wash water, the indigo dye molecules that were physically trapped within that specific layer are effortlessly released and washed away. Because the large cellulase enzyme molecules target only the outermost accessible fibrils and are physically too large to penetrate deeply into the tightly woven core of the yarn, the primary structural integrity and tensile strength of the main fiber remain completely intact and undamaged. A minimal amount of mechanical tumbling is still required inside the machine to help physically detach the enzymatically weakened fibers, but the heavy reliance on destructive abrasive pumice stones is either drastically reduced to a fraction of the original volume or entirely eliminated. This highly targeted, purely enzymatic hydrolysis achieves the exact identical high-contrast fading, the desired aged look, and the supreme fabric softness of traditional stone washing, but it totally preserves the overall strength of the garment, eliminates catastrophic machine wear, and completely removes the costly operational bottleneck of extracting toxic stone dust and fragments. Formulators typically utilize both acid cellulases, operating at pH 4 to 6, which provide highly aggressive abrasion and rapid fading, and neutral cellulases, operating at pH 6 to 8, which are specifically engineered to minimize a highly undesirable phenomenon known as backstaining, where the enzymatically released indigo dye floating in the wash liquor chemically reattaches and redeposits onto the pristine white weft yarns of the denim, muddying the contrast. Biopolishing and catalytic bleach cleanup. The exact same mechanism of precise cellulase hydrolysis is also utilized in a completely distinct, highly valuable textile finishing process universally known as biopolishing. Beyond heavy denim, many delicate cotton, flax, hemp, viscose, and cellulosic blended fabrics suffer from inherent structural imperfections resulting from the mechanical stress of the initial spinning and weaving processes. These microscopic imperfections manifest as loose, tiny, protruding microfibrils that stand up vertically from the main body of the yarn, creating a hazy, fuzzy surface. During routine consumer wear and laundering, everyday friction causes these loose microfibrils to tangle together into highly unsightly hard little balls known as pills, which trap dirt and severely degrade the fabric's appearance, making it look cheap and worn out. During the biopolishing finishing step, highly concentrated acid cellulases are applied to the fabric bath to perform what is essentially a microscopic enzymatic singeing operation. The cellulase enzyme molecules preferentially locate and bind to the loose, protruding microfibrils because these tiny hairs present a vastly greater and more highly accessible surface area compared to the tightly bound, highly ordered main yarn structure. The enzymes rapidly hydrolyze the cellulose precisely at the base of the microfibrils, cleanly severing them and detaching them completely from the fabric. The result is a permanently smooth, completely lint-free and fuzz-free textile that aggressively resists future pilling. Because the fuzzy, light-scattering surface layer has been entirely eliminated, the fabric drapes much more fluidly over the body, feels exceptionally soft and luxurious against the skin, and exhibits a highly lustrous, incredibly vibrant color profile that mimics the expensive look of traditional chemical mercerization, completely rejuvenating the garment and ensuring it looks brand new even after repeated washings. Enzymes also massively streamline the intense chemical preparation of textiles that must occur prior to the dyeing process. Raw cotton arriving at the mill contains natural yellowish pigments, waxes, and impurities that must be aggressively bleached, typically utilizing incredibly high concentrations of boiling hydrogen peroxide to remove the color and achieve a pure, uniform white base suitable for vibrant dyeing. However, this creates a massive secondary problem. Before the bright white fabric can be dyed with expensive reactive dyes, absolutely every microscopic trace of residual hydrogen peroxide must be entirely eradicated from the cloth. If any peroxide remains, the highly reactive oxygen species will immediately attack, oxidize, and completely destroy the incoming dye molecules, resulting in ruined, patchy, uneven coloration and massive financial losses for the mill. Historically, neutralizing this clinging peroxide required the textile mill to use massive, incredibly wasteful volumes of hot rinsing water, or the application of harsh, expensive chemical reducing agents that further complicated the bath chemistry. To radically optimize this process, modern textile manufacturers now deploy a highly specific oxidoreductase enzyme known as catalase. Catalase is an incredibly fast-acting enzyme explicitly and solely designed by nature to dismantle hydrogen peroxide. When a small dose of liquid catalase is introduced to the post-bleach wash bath, the enzyme intercepts the residual hydrogen peroxide molecules and instantaneously catalyzes their complete decomposition into completely harmless liquid water and bubbling oxygen gas. Because the catalase enzyme operates with such profound, unmatched speed and absolute chemical specificity, the entire concentration of peroxide is completely and safely neutralized in a fraction of the time. This brilliant biological intervention allows the manufacturer to proceed directly to the sensitive dyeing phase in the exact same bath without altering the final color shade, completely eliminating the need for extensive water-intensive rinsing protocols, drastically lowering energy consumption, and significantly reducing overall factory processing times. Cosmetic precision, advanced enzymatic exfoliation. The fundamental principles of precision enzymatic hydrolysis applied to industrial textiles are remarkably analogous to their advanced application in high-end dermatological treatments and cosmetic skincare formulations. The outermost layer of human skin, biologically known as the stratum corneum, acts as the body's primary protective barrier against the environment. This vital layer is composed primarily of dead, highly flattened skin cells known as keratinocytes. These dead cells are densely packed with keratin, an incredibly tough, highly resilient structural protein, and they are tightly bound and cemented together by an intricate glue-like network of proteinaceous structures known as desmosomes. In healthy, youthful skin, these dead cells naturally flake off in a process called desquamation. However, as the skin ages, or as it endures persistent environmental stress and UV damage, this natural shedding process slows down drastically. The dead cells begin to accumulate and stack up on the surface, resulting in a chronically rough, uneven texture, a dulled gray appearance, and deeply congested pores that frequently lead to acne breakouts. Traditional cosmetic methods for removing this dead layer rely on two blunt approaches: mechanical exfoliation or chemical exfoliation. Mechanical exfoliants utilize physical friction, employing harsh, gritty scrubs containing crushed walnut shells or microplastics that literally sand the dead skin away. This primitive method frequently causes invisible, damaging micro-tears in the living epidermis, leading to severe irritation and bacterial infection. Chemical exfoliants, conversely, utilize high concentrations of alpha-hydroxy acids, or BHAs. These acids operate by drastically lowering the overall pH of the skin's surface to incredibly acidic levels, indiscriminately burning and dissolving the cellular glue. While effective, this blunt chemical trauma frequently triggers severe erythema, redness, intense stinging, inflammation, and profound disruption of the delicate moisture barrier, particularly in individuals with sensitive or rosacea-prone skin types. Enzymatic exfoliants offer a highly sophisticated, biochemically precise, and incredibly gentle alternative to these harsh traditional methods. Cosmetic formulators utilize specific, highly active proteolytic enzymes extracted primarily from botanical sources and agricultural byproducts to achieve perfectly controlled skin resurfacing. The most prominent and widely utilized among these cosmetic enzymes are papain, sourced from the milky latex of unripe papaya fruit, bromelain, extracted efficiently from the discarded stems and peels of pineapples, and ficin, derived from the latex of the fig tree. These remarkable enzymes belong to the cysteine protease family. They function not by altering the pH of the skin, but by directly, specifically targeting and hydrolyzing the actual peptide bonds within the keratin proteins that cement the dead skin cells firmly to the epidermal surface. When an enzymatic peel or cleansing gel is applied to the face, these proteases act like microscopic scalpels. They selectively and gently digest the specific structural proteins holding the outermost keratinocytes in place, essentially ungluing the dead cells. Unlike harsh chemical acids, which indiscriminately attack everything they touch, these biological enzymes operate optimally and efficiently very near the skin's natural, comfortable pH level. By specifically snipping only the dead protein linkages, the enzymes allow the entire layer of dull, dead cells to seamlessly detach and wash away down the sink, instantly revealing the much smoother, highly refined, and deeply radiant layers of newer skin beneath. Furthermore, these specific botanical enzymes possess incredibly broad and highly beneficial functional profiles that extend far beyond simple exfoliation. Bromelain, for instance, possesses a highly specific, broad substrate specificity and exhibits incredibly potent natural anti-inflammatory and antimicrobial properties. It actively works to inhibit pro-inflammatory cytokine activity on the skin, making it exceptionally suited and highly prized by estheticians for treating highly stressed, acne-prone, or redness-prone skin types, providing deep exfoliation without ever inducing secondary trauma or swelling. Ficin, which possesses both profound protease and peroxidase activity, offers immense antioxidant benefits and actively assists in reducing localized melanin synthesis, contributing directly to a brighter, much more uniform skin tone and the fading of hyperpigmentation. Papain is highly valued for its intense, deep cleansing keratolytic activity, improving the penetration pathways for other expensive active cosmetic ingredients such as vitamin C serums or hyaluronic acid to reach the deeper layers of the epidermis where they are most effective. By strictly restricting their hydrolytic activity only to the keratinized, non-living carriage of the surface and ceasing activity before damaging living cells, these enzymatic exfoliants perfectly preserve the integrity of the underlying living tissue, enabling safe, frequent use and delivering unparalleled cosmetic results. The science of scale, synthesis, purification, and extreme stabilization. The transition from simply recognizing the theoretical utility of an enzyme in a laboratory beaker to successfully deploying it on a massive commercial scale inside a laundry detergent pod, across a sprawling bakery floor, or stabilized within a cosmetic peel requires an extraordinarily complex, highly optimized industrial infrastructure. Enzymes are, by their very biological nature, incredibly fragile macromolecules. Outside of their native, highly regulated cellular environments, their delicate three-dimensional folded structures are highly susceptible to rapid, irreversible denaturation and total loss of catalytic activity when exposed to heat, ambient moisture, extreme mechanical shear, and aggressive chemical antagonism from other ingredients. Scaling up their mass production and meticulously engineering their extreme stability for long-term commercial shelf life represents a monumental triumph of modern biochemical engineering, downstream processing, and advanced material science. Upstream processing and microbial fermentation. The industrial synthesis of enzymes begins with upstream processing, a methodology that relies entirely on harnessing the metabolic machinery of highly optimized, often recombinant microorganisms. Rather than attempting to extract enzymes from raw plant or animal tissues, a primitive process that is economically unfeasible, highly wasteful, and yields wildly inconsistent volumes and purities, modern manufacturers cultivate specific elite strains of bacteria and fungi. Microorganisms such as species of Bacillus, Aspergillus, and Trichoderma serve as highly efficient microscopic factories. Through advanced biotechnology, these microbes are genetically programmed and meticulously optimized to hyper-express the exact desired target enzyme in incredibly massive quantities, far exceeding their natural biological requirements. This immense biological cultivation occurs within massive, towering industrial bioreactors utilizing two primary distinct methodologies: submerged fermentation, SMF, and solid-state fermentation, SSF. Submerged fermentation is the absolute dominant paradigm for large-scale, highly automated commercial operations, utilized to produce the vast majority of detergent and food enzymes. In this highly controlled liquid process, the billions of microorganisms are suspended in a vast circulating liquid nutrient broth. This broth contains incredibly precise, scientifically calculated ratios of carbohydrate carbon sources, like glucose or agricultural syrups, nitrogen, essential vitamins, and trace minerals necessary for explosive microbial growth. The liquid bioreactors are strictly sealed, highly controlled environments where critical metabolic parameters such as internal temperature, pH levels, dissolved oxygen concentration, and mechanical agitation speed are continuously monitored by sensors and adjusted in real time by computers. The constant, vigorous agitation by massive impellers ensures perfect, uniform nutrient distribution and maximizes the crucial oxygen transfer necessary for the aerobic microbes to thrive, multiply, and continuously secrete the target enzymes directly out of their cells and into the surrounding liquid medium. Conversely, solid-state fermentation is utilized predominantly for the production of specific fungal enzymes that strictly require growth conditions mimicking their natural terrestrial habitats, such as fungi that naturally grow on decaying plant matter. In this process, there is no vast pool of free-flowing liquid. Instead, the microorganisms are cultivated directly on the surface of a solid, porous, moistened substrate, frequently utilizing cheap agricultural byproducts such as wheat bran, sugarcane bagasse, or rice husks. The solid substrate provides both the necessary complex carbon food source and a critical physical anchor for the branching fungal mycelia to penetrate and grow into. As the fungi consume the solid waste, they secrete incredibly high concentrations of enzymes directly onto the solid matrix to digest it. While solid-state fermentation is notoriously difficult to scale because it demands incredibly complex engineering to control internal moisture gradients and dissipate the massive heat generated by the dense fungal growth, it frequently yields highly concentrated, incredibly robust enzyme complexes, perfectly tailored for specialized applications, such as the aggressive breakdown of lignocellulosic biomass or advanced baking applications. Downstream processing, isolation, and extreme purification. Once the fermentation cycle reaches its absolute peak enzyme concentration and the microbes have exhausted their food supply, the entire operation shifts immediately to downstream processing. Downstream processing is a rigorous, highly complex sequence of physical and chemical unit operations meticulously designed to isolate, safely concentrate, and highly purify the incredibly fragile biocatalyst away from the complex, murky biological soup of the fermentation broth. The very first critical step is harvesting, which involves physically separating the billions of microbial cells, their broken cellular debris, and any unconsumed solid nutrients from the liquid medium that now contains the secreted enzymes. This is typically and most efficiently achieved through high-speed industrial centrifugation. The centrifuges spin the broth at extreme velocities, exploiting the massive centrifugal force to drive the dense, heavy cellular mass outward and to the bottom of the vessel, forming a thick paste, while allowing the lighter, clear, enzyme-rich liquid to be smoothly drawn off the top. Following this primary physical separation, the clarified liquid undergoes a strict cascade of advanced membrane filtration techniques to remove microscopic impurities and drastically concentrate the product. Microfiltration utilizes highly engineered porous membranes to catch any remaining microscopic bacterial debris or stray spores, ensuring a completely sterile, clarified liquid stream. Subsequently, the massive volumes of liquid must be reduced. This is achieved through ultrafiltration and tangential flow filtration, TFF, which are employed to execute precise buffer exchange and massive up concentration. Ultrafiltration membranes feature highly specific microscopic molecular weight cutoffs. When the liquid is pumped across these membranes under high pressure, small molecules like water, stray salts, and tiny metabolic byproducts are forced through the pores and discarded as permeate. However, the much larger, bulky enzyme proteins are physically too big to pass through the pores. They are retained, swept along the membrane surface, and continuously concentrated into a thick, highly potent liquid syrup. If the final consumer application demands extreme pharmaceutical-grade purity, such as in certain high-grade cosmetic formulations, specialized transparent beverages, or advanced dairy processing where absolutely no off-flavors can be tolerated, the concentrated liquid enzyme is routed through massive chromatography columns. These stainless steel columns are packed with specialized stationary chemical resins that act like molecular magnets. As the liquid flows through, the resins specifically bind the target enzyme based on highly specific biochemical criteria, such as the enzyme's unique surface charge, its hydrophobicity, or its exact molecular affinity. While the precious enzyme is locked onto the resin, all remaining extraneous host cell proteins, stray DNA, and contaminants are completely washed away by buffer solutions. Finally, a change in the buffer chemistry releases the enzyme from the resin, yielding a product of absolute, uncompromised purity. The mechanism of liquid formulation stabilization. For enzymes destined for liquid consumer products, particularly heavy-duty liquid laundry detergents, the formulation presents a profound, seemingly impossible biochemical paradox. Ensuring the absolute stability of a highly reactive mixture of enzymes within a harsh, surfactant-heavy aqueous environment over a prolonged shelf life of up to 2 years. The primary issue is the presence of proteases. Because proteases are specifically designed by nature to aggressively seek out and completely degrade proteins, they inherently view all other enzymes in the detergent bottle, like the lipases, amylases, cellulases, and even other protease molecules, as totally viable food substrates. If left uncontrolled and fully active in a warm liquid detergent sitting on a warehouse shelf, the proteases will engage in rapid, catastrophic autoproteolysis. They will literally digest and cannibalize the entire enzymatic system within a matter of days, rendering the costly detergent completely inactive and useless long before the consumer ever purchases it. To brilliantly circumvent this destructive cannibalistic process, detergent formulators employ highly sophisticated built-in chemical stabilization systems. The most prominent and effective system relies on the precise combination of boron compounds, such as boric acid or specialized borate salts, and polyols, such as propylene glycol or heavy glycerol. This unique chemical system functions through a fascinating mechanism of reversible competitive inhibition that specifically targets and neutralizes the active site of the destructive protease. Advanced X-ray crystallography studies of these stabilized detergent mixtures have revealed exactly how this works at the atomic level. The boron atom interacts directly with the highly reactive catalytic serine residue located deep within the protease's active site. The boron atom seamlessly adopts a specific tetrahedral coordination, forming a temporary, secure covalent bond directly with the oxygen atom of the serine residue. This specific structural configuration is an act of incredible biochemical deception. It is critical because it perfectly mimics the exact tetrahedral intermediate transition state that occurs naturally during the true hydrolysis of a peptide bond in a protein stain. One of the oxygen atoms from the boric acid slides in and occupies the enzyme's oxyanion hole, a specific region of the active site designed to stabilize the negative charge of the transition state during a real reaction. Meanwhile, another oxygen atom occupies the site normally reserved for the leaving group of the target substrate. The absolute stability of this fake transition state analog is further tightly reinforced by strong hydrogen bonding from surrounding amino acid residues, essentially tricking the protease into thinking it is in the middle of a reaction and effectively locking the protease in a frozen, dormant state. The dangerous enzyme is completely safely neutralized during its entire storage life. However, this masterful inhibition is strictly and exquisitely concentration dependent. When the consumer finally pours the thick liquid detergent into the washing machine drum, the vast, sudden influx of gallons of wash water rapidly and massively dilutes the formulation. The localized concentration of the boron and polyol molecules plummets instantly. Deprived of concentration pressure, the reversible borate complex shatters and dissociates away from the enzyme. The protease is instantly liberated, its active site is perfectly restored to its pristine condition, and it immediately begins its intended aggressive function of attacking real protein stains within the wash liquor. Advanced granulation and extreme dry stabilization. For solid consumer applications, such as aggressive powdered laundry detergents, highly alkaline automatic dishwasher tablets, or bulk baking mixes, the purified liquid enzyme concentrate must undergo an even more rigorous transformation. It must be converted into a perfectly dry, free-flowing, dust-free powder, or macroscopic granule. The most formidable challenge here is achieving total dehydration without inflicting catastrophic thermal denaturation upon the fragile protein structures during the intense drying process. To achieve this delicate balance, manufacturers rely heavily on advanced spray drying and massive fluid bed granulation technologies. In the spray drying process, the thick, concentrated liquid enzyme liquid is pumped under immense pressure and rapidly atomized through fine nozzles into a microscopic mist inside a massive, towering cyclonic heated chamber. The enormous exponential increase in surface area provided by the millions of tiny droplets allows the water solvent to evaporate almost instantaneously upon contact with the hot air. Because the physical process of evaporation rapidly absorbs massive amounts of heat energy from the immediate surroundings, the actual core temperature of the microscopic enzyme particle remains remarkably low and perfectly safe, preventing the fragile, heat-sensitive protein structure from cooking or denaturing before it drops to the cool bottom of the chamber as a perfectly dry powder. To further ensure survival, formulators meticulously mix the liquid enzyme with specific stabilizing carrier molecules, such as trehalose, heavy maltodextrin, or lactose sugars, prior to atomization. As the water flashes off, these specific sugars rapidly crystallize and form a hard, protective, glassy matrix entirely encasing the enzyme molecules. This rigid sugar glass physically restricts the movement of the protein chains, shielding their delicate three-dimensional folding structures from intense mechanical shear and thermal stress. However, for the absolute harshest commercial environments, such as highly concentrated, heavily alkaline, bleach-containing powdered detergents, where the enzymes will sit directly next to destructive oxidizing chemicals for months, simple spray-dried powders are vastly insufficient. They would be oxidized and destroyed in days. For these extreme applications, the enzyme must be heavily armored. This is achieved through the creation of highly engineered macroscopic multi-layered particles, universally known in the industry as T-granules. Using massive high-shear mixers and industrial fluid bed coaters, the concentrated liquid enzyme is slowly sprayed onto a solid, inert core seed, often composed of finely ground cellulose fibers, tough binders, and heavy salts. This builds up a highly concentrated, dense active enzyme layer around the core. Once the precious enzyme layer is firmly established, the manufacturing equipment does not stop. It sequentially and meticulously applies multiple, completely distinct protective coating layers over the entire granule, like the layers of a jawbreaker candy. These thick, protective shells frequently consist of dense polyethylene glycol waxes, impermeable kaolin clay, bright white titanium dioxide, and highly specialized polymeric binders. The resulting heavy, multi-layered granule acts as an absolutely impenetrable fortress. The thick, waxy shell physically and chemically isolates the sensitive enzyme core from ambient humidity, destructive atmospheric oxygen, and most importantly, the highly aggressive hydrogen peroxide-releasing bleaching chemicals that are packed right next to it in the detergent box. To further enhance the physical handling characteristics in the factory and to absolutely prevent the generation of microscopic, hazardous enzyme dust that could cause severe allergic reactions in manufacturing workers or consumers during pouring, the outermost layer of the tea granule is frequently coated with a thin layer of liquid lubricant, such as a heavy mineral oil or a non-ionic surfactant. This final lubricant layer ensures the heavy granules flow smoothly like liquid sand, resisting any fracturing, chipping, or dust formation upon aggressive collision during shipping and handling. It is only when the consumer finally submerges the detergent powder into the hot, churning water of a washing machine that these complex protective polymer and wax shells rapidly and completely dissolve, finally releasing the pristine, fully active, perfectly preserved enzymes to initiate their highly targeted molecular cleaning functions. The successful deployment of these microscopic proteins across diverse global industries is underpinned by massive, continuous advancements in upstream microbial fermentation and highly complex, rigorous downstream isolation procedures. The ability of modern science to lock a dangerous protease in a dormant transition state using competitive boron inhibitors for liquid formulations, or to construct massive, multi-layered armored tea granules to shield fragile amylases from oxidative bleach in dry powders, demonstrates the extraordinary, unprecedented lengths to which biochemical engineering has evolved to master the exacting science of scale. As the global demand for highly specialized, highly efficient, and deeply refined consumer goods continues to grow exponentially, the continued molecular manipulation, structural optimization, and vast industrial deployment of these biological engines will undoubtedly remain the absolute cornerstone of advanced, high-performance manufacturing for the foreseeable future. Integration of industrial enzymes into modern hardware and digital systems. While traditional industrial applications confined these biological catalysts to the domains of food processing, textile modification, and pharmaceuticals, their unique mechanical capabilities are now being weaponized for high-tech, solid-state applications. Because enzymes can target specific molecules with atomic precision, operate autonomously, and facilitate highly complex molecular exchanges without the need for extreme temperatures or aggressive physical forces, they offer distinct mechanical advantages over traditional physical and chemical engineering methods. The transition of enzymes from biological entities to highly optimized industrial hardware components was made possible largely through the advent of directed evolution, a revolutionary bioengineering technique. Natural evolution of enzymes occurs over millions of years as organisms adapt to new environments. Directed evolution, however, is a highly accelerated, man-made procedure built on precise molecular manipulation that moves the evolution process into the laboratory. This iterative procedure involves the identification of a starting protein, the diversification of its genetic code through induced random mutations, and the rigorous functional screening of the resulting variants to identify the specific enzyme that performs best under targeted industrial conditions. This cycle of mutation and selection is repeated endlessly, until the enzyme achieves a satisfactory performance level in terms of catalytic activity, thermal stability, or chemical specificity. The power of directed evolution in the realm of material science and semiconductor engineering was definitively proven through the groundbreaking work of researchers like Francis Arnold, who utilized the technique to force enzymes to perform chemical reactions completely unknown to the natural world. Silicon constitutes a massive portion of the Earth's crust and is the foundational material of the entire global technology sector. Yet absolutely no life form on Earth is known to possess the biological ability to forge bonds between carbon and silicon. To bridge this gap, engineers hypothesized that specific heme proteins might possess a latent, underlying capacity to catalyze carbene insertion into silicon-hydrogen bonds. By taking a highly stable enzyme, specifically cytochrome C from the bacterium Rhodothermus marinus, researchers utilized directed evolution to iteratively mutate its active site. Through multiple generations of selective pressure, they discovered specific mutations that altered the physical flexibility of the protein, enabling the engineered enzyme to form carbon-silicon bonds with staggering efficiency. The resulting variants catalyzed these highly complex reactions with thousands of total turnovers, exhibiting absolute chemoselectivity and producing highly pure organosilicon products. This achievement proved that nature's protein repertoire is highly evolvable and poised for mechanical adaptation. With only a few strategic mutations, existing proteins can be completely repurposed to efficiently forge chemical bonds not found in biology, granting engineers access to entirely new areas of chemical space and providing a highly controlled method for synthesizing advanced semiconductor precursors and organosilicon components. Wearable tech and biosensors, translating biology into binary code. The modern consumer relies heavily on wearable technology, ranging from smartwatches and continuous glucose monitors to intelligent fitness patches and transdermal diagnostic arrays to track physiological data in real time. The core function of these devices is essentially an act of continuous, highly precise translation. They must bridge the immense gap between the analog, chaotic chemical signals of the human body and the discrete digital electrical signals processed by silicon computer microchips. This highly complex translation is achieved through the integration of enzymatic biosensors, which serve as the primary mechanical interface between human biology and consumer electronics. The history of this technological intersection dates back to 1956, when Leland Clark presented his foundational research on the oxygen electrode, which would eventually become known as the Clark electrode. This early hardware laid the absolute groundwork for biosensing technology. By 1965, this concept was expanded to specifically target glucose by pairing the electrode with redox enzymes. The fundamental architecture established in these early decades slowly evolved, moving from large hospital-based analytical machines to portable test strip meters, and finally culminating in the highly miniaturized continuous glucose monitoring systems that were first approved for commercial use in the late 1990s. Today, these systems have been refined to operate continuously on the skin or subcutaneously, communicating directly with consumer smartphones and smartwatches. To fully grasp how a modern smartwatch or a continuous glucose monitor reads a biological marker, one must examine the multi-layered microscopic architecture of the biosensor itself. A typical wearable electrochemical sensor consists of a highly specific biorecognition element seamlessly merged with an electronic transducer. In these advanced consumer devices, the biorecognition element is a densely packed, immobilized layer of specific enzymes chosen for their unique ability to react exclusively with a single target biomarker present in human biofluids, such as sweat, saliva, or interstitial fluid. For example, in continuous glucose monitors, the primary biological catalyst deployed is the enzyme glucose oxidase, chosen for its extreme specificity to glucose and its high resilience to fluctuations in ambient temperature and fluid acidity. When the user's interstitial fluid or sweat comes into physical contact with the active sensing layer, the glucose oxidase chemically binds with the ambient glucose molecules. Through a highly specific enzymatic reaction, the protein systematically strips electrons from the glucose, generating a highly localized and measurable electrical current. The mechanical genius of this enzymatic system lies in its direct mathematical proportionality. The amount of electrical current generated by the millions of immobilized enzymes is perfectly correlated with the absolute concentration of the biomarker in the fluid, meaning a higher glucose level results in a proportionally stronger, faster electrical output. However, capturing this minute, highly sensitive electrical output and feeding it into a microprocessor requires sophisticated hardware integration. This stringent requirement has led to the development and aggressive miniaturization of the enzyme field effect transistor, commonly referred to as the ENFET. An ENFET takes the fundamental building block of all modern computing, the metal oxide semiconductor transistor, and merges it directly with an active enzymatic layer. The fabrication of an ENFET involves highly complex nanoscale microelectronic processes that are executed in advanced semiconductor foundries. During the manufacturing of the silicon wafer, standard complementary metal oxide semiconductor processes are utilized to create the foundational transistor base. This involves the meticulous doping of specific geometric zones within the silicon crystal lattice with elements like boron and arsenic to create the source and drain regions of the transistor. Above the extremely thin gate oxide of the transistor, engineers synthesize a nanostructured compound, frequently utilizing titanium dioxide or highly aligned carbon nanotubes using advanced anodization and deposition techniques. The target enzymes, such as glucose oxidase or lactase oxidase, are chemically anchored directly into this nanostructured layer. Immobilizing the enzyme onto the hard silicon surface is a critical, highly difficult engineering challenge. If the enzymes detach and float away, or if they lose their precise three-dimensional folded structure during the attachment process, the sensor immediately fails. Therefore, hardware engineers utilize a complex combination of physical adsorption, encapsulation within polymer matrices, and sophisticated cross-linking chemicals to lock the proteins permanently into the transistor's matrix. These techniques ensure the enzymes remain firmly attached to the hardware while retaining their full functional reactivity and the necessary physical flexibility to execute their catalytic cycles. When the target biomarker in the user's sweat or interstitial fluid interacts with the immobilized enzyme on the ENFET, the resulting chemical reaction creates a highly localized fluctuation in the electrical charge at the absolute surface of the chip. This microscopic, highly localized shift in surface potential directly modifies the electrical conductivity of the underlying silicon channel, situated between the source and the drain within the transistor. By altering how easily electrons can flow through the solid-state hardware, the biological enzyme effectively acts as a physical gate switch, controlling the flow of digital information based purely on the specific chemical composition of the user's bodily fluid. To complete the necessary electrical circuit, these sophisticated devices often integrate a solid-state silver and silver chloride reference electrode directly onto the microchip, alongside the functional transistor. Translating this microscopic, highly variable shift into the readable, actionable data displayed on a smartwatch interface requires rigorous and continuous electronic signal processing. The raw electrical output generated by the EFET is an analog signal, meaning it is continuous and often clouded by massive amounts of electrical interference and biological noise. The wearable device first routes this exceptionally weak analog current through an internal microelectronic amplifier to boost its total amplitude. Next, the signal passes through sophisticated filtering circuits that mathematically strip away the background noise caused by user movement, ambient temperature fluctuations, and the presence of other non-target chemicals that might inadvertently interact with the electrode. The purified, amplified analog signal is then fed directly into a critical piece of solid-state hardware known as an analog-to-digital converter. This converter samples the continuous analog voltage at rapid, precisely timed intervals, assigning a discrete binary value, a specific series of ones and zeros, to each measured voltage level. The specific resolution of this converter dictates the ultimate precision of the device. Higher resolution converters assign far more precise digital values, allowing the smartwatch's central processing unit to calculate the exact concentration of the biomarker with absolute clinical accuracy before displaying it on the screen. A major engineering hurdle in wearable bioelectronics is signal degradation over time and physical interference at the sensor surface. Enzymes are highly delicate, complex structures that can unfold, denature, or degrade when exposed to excessive mechanical friction, drastic changes in pH, or fluctuating ambient temperatures. Furthermore, the sensors are continuously subject to biofouling, a mechanical process where proteins, lipids, and cellular debris from the human skin clog the sensor's surface, physically blocking the target biomarkers from reaching the enzymatic layer. To combat this persistent issue, hardware engineers utilize highly advanced enzyme encapsulation techniques. Rather than simply coating the bare electrode, the enzymes are often permanently trapped within electropolymerized polymer meshes, synthetic hydrogels, or complex membrane structures. These synthetic polymer cages act as strict physical size exclusion barriers, allowing tiny target molecules like glucose or lactate to slip through the molecular pores and reach the active enzyme, while strictly blocking larger fouling proteins and cellular debris from compromising the delicate sensor. Additionally, the signal-to-noise ratios and absolute detection limits in modern wearable devices are being dramatically enhanced through the use of three-dimensional nanostructured electrodes. Traditional flat, planar electrodes severely limit the total number of enzymes that can be packed into a given geometric area, leading to weak baseline signals. By utilizing incredibly complex nanostructures, such as heavily doped silicon nanowires, aligned carbon tubes, or nanoporous gold architectures, engineers can exponentially increase the available active surface area of the electrode without increasing the overall macroscopic size of the sensor. This allows millions of additional enzyme molecules to be wired directly to the circuit, creating a massively parallel sensing array that generates a substantially stronger, highly reliable baseline signal. The specific nanoporous geometry also physically reduces electrical charge screening at the interface, ensuring that the transfer of electrons from the reacting enzyme to the hardware is virtually instantaneous and highly efficient. Beyond simple glucose and fitness tracking, this deep enzymatic hardware integration is pushing the boundaries of complex, multivariable diagnostics and advanced biocomputing. Researchers are actively developing flexible, bandage-type wearable sensors embedded with highly specific enzymes, like tyrosinase. This specific enzyme is used to electrochemically detect and quantify molecular markers directly associated with aggressive melanoma, providing rapid, point-of-care screening directly on the surface of the skin by measuring the specific byproduct of the enzymatic reaction. Furthermore, the integration of these sophisticated sensors into smart clothing, known as e-textiles, is creating active garments capable of continuously monitoring biomechanics, fluid loss, and physiological signals simultaneously. In these highly active textiles, conductive metallic threads act as the primary electrodes, and targeted enzymes are directly woven or printed into the fabric alongside microscopic fluidic channels that constantly wick sweat away from the body and route it directly to the active sensor arrays. The integration of enzymes into silicon has also opened the door to true biomolecular computing, where the enzymes themselves perform digital logic operations before the signal even reaches the microprocessor. By combining multiple specific enzymes, researchers have constructed functional biological logic gates, including AND, OR, and XOR operations. For example, a functional AND gate can be constructed by carefully orchestrating a cascade of reactions using multiple enzymes operating in concert. If the system requires two specific inputs, such as two distinct biomarkers, the first enzyme reacts with the first marker to produce an intermediate chemical. The second enzyme requires both the intermediate chemical and the second biomarker to execute its reaction and produce the final measurable electrical output. If only one marker is present, the cascade halts and no signal is generated, perfectly mimicking the binary logic of a silicon transistor array. These enzymatic logic networks can even be optimized to reduce analog signal noise by utilizing co-substrates that create a sigmoid response curve, acting as a biological filter that prevents false positive readings from weak or ambient signals. Through these meticulous hardware integrations and advanced biocomputing architectures, the biological chaos of human physiology is successfully tamed, digitized, and translated into crisp, actionable data streams. Enzymatic data storage, the molecular hard drive. As global digital infrastructure continues to expand at an unprecedented and accelerating rate, the entire technology sector is rapidly approaching a critical, insurmountable physical threshold regarding data storage capacity. Traditional data storage media, such as magnetic hard disk drives, optical disks, and solid-state silicon flash memory, face hard, fundamental physical limits regarding exactly how densely they can pack binary information. Furthermore, these conventional hardware formats possess relatively short functional lifespans, physically degrading over decades and requiring massive, energy-intensive data centers to constantly copy, migrate, and maintain endless archives to prevent catastrophic data loss. In response to this looming exponential data storage crisis, the computing industry is aggressively pursuing a radically different, biologically derived storage medium, deoxyribonucleic acid, or DNA. DNA is nature's ultimate, highly optimized information storage system, refined and perfected over billions of years of biological evolution. While traditional computers encode data using a binary system of changing electrical states represented by zeros and ones, DNA encodes immense amounts of information using a highly efficient quaternary structural system based on the physical arrangement of four specific nucleotide bases: adenine, thymine, cytosine, and guanine. The theoretical data storage density of this biological polymer is staggering. A single gram of synthetic DNA can hold theoretically hundreds of petabytes of digital data, equating to hundreds of millions of high-definition movies. Theoretically, all the world's recorded digital information, the entirety of the internet, and all historical archives could be archived within a physical volume the size of a standard shoebox. Furthermore, if kept away from moisture and extreme radiation, DNA remains structurally stable for hundreds or even thousands of years, completely eliminating the need for constant energy-intensive data migration. However, harnessing DNA as a functional, rapid read and write hard drive requires the profound ability to manufacture specific custom sequences of nucleotides rapidly, flawlessly, and at a massive industrial scale. Historically, synthesizing custom DNA sequences relied entirely on a highly established cyclical four-step chemical reaction known as the phosphoramidokide method. Originally developed in the early 1980s, this is a cyclical four-step chemical reaction that systematically adds desired nucleotides to a growing oligonucleotide chain that is physically immobilized on a solid support matrix. While this legacy chemical process was highly effective and foundational for creating short strands of genetic material for basic research, It is intrinsically slow and highly prone to accumulating structural errors when attempting to build the extremely long sequences required for meaningful digital data storage. Despite decades of optimization, the stepwise chemical yield of the phosphoramidinide method plateaus around 99.5%. While this sounds efficient, when attempting to build a continuous chain of thousands of bases, that minute error rate compounds exponentially, limiting the practical maximum length of a synthesized strand to roughly 200 nucleotides before the total yield of correct sequences drops to unusable levels. Furthermore, this legacy chemical process requires harsh, volatile liquid solvents, hazardous reagents, and strict anhydrous environments. The harsh acids and bases utilized repeatedly during the deprotection and coupling phases physically degrade the final DNA product, causing high rates of truncated, broken species that corrupt the stored data. Attempting to manage this aggressive liquid chemistry within the compact, high-speed constraints of consumer or enterprise hardware is functionally impossible. To overcome these severe mechanical limitations, increase data density, and accelerate writing speeds, the technology industry is transitioning entirely to enzymatic DNA synthesis, a revolutionary process that utilizes highly specialized proteins to write digital data directly into biological polymers. The primary biocatalyst driving this high-density data revolution is terminal deoxynucleotidal transferase, commonly referred to as TDT. In nature, TDT is a highly unusual, specialized DNA polymerase originally discovered in the 1960s within the immune system of vertebrates, specifically operating in calf thymus. Unlike traditional DNA polymerases, which strictly require an existing matching template strand to copy information from, TDT possesses the incredibly unique mechanical ability to build entirely new DNA strands completely from scratch. It continuously and indiscriminately adds deoxynucleotide triphosphates to the 3' hydroxyland of a growing single-stranded DNA chain in a completely template-independent manner. This highly specific, untemplated synthesis capability makes the highly engineered, directed evolution version of the TDT enzyme the absolute perfect biological printhead for a high-speed molecular hard drive. To write a digital file, such as a high-resolution photograph, a complex software program, or a text document into a DNA hard drive, the file's raw binary code is first translated by a complex computer encoding algorithm into a specific sequence of the 4 DNA bases. This generated base sequence serves as the precise step-by-step blueprint for the enzymatic synthesis. The engineered TDT enzyme is then deployed into the system to physically construct the molecule. However, because natural, unengineered TDT works incredibly rapidly and uncontrollably, stringing random bases together indiscriminately to create diverse immune receptors, hardware engineers must assert precise, absolute mechanical control over the enzyme's actions to ensure the data is written flawlessly. This control is achieved using highly engineered, reversibly terminated nucleotides. During the active writing cycle, the targeted TDT enzyme is introduced to a solid silicon or glass support, which is uniformly coated with a microscopic initiator DNA sequence that provides a physical, stable foothold for the reaction to begin. A controlled batch of the specific nucleotide dictated by the digital blueprint is introduced into the microfluidic chamber. The TDT enzyme physically grabs the nucleotide and rapidly catalyzes the bond, attaching it to the growing DNA strand. Because this specifically engineered nucleotide possesses a proprietary chemical terminator cap on its structure, the TDT enzyme is physically blocked from adding any subsequent bases, halting the reaction instantly after a single addition. The system briefly pauses, A mild, non-destructive chemical wash is applied to gently cleave and remove the terminator cap from the newly added base, and the rapid cycle repeats with the introduction of the next specific nucleotide in the sequence. This step-by-step enzymatic addition yields astonishingly high coupling efficiencies, far exceeding legacy chemical methods, allowing for the rapid creation of exceptionally long, highly accurate data strands without the need for extreme temperatures, vacuum chambers, or highly aggressive degrading liquid chemistry. Furthermore, this advanced enzymatic process can be optimized to operate effectively at higher temperatures, up to 70 degrees Celsius. Operating at this elevated temperature physically melts away complex secondary structures and hairpin loops that naturally form in long DNA chains, allowing the system to easily synthesize traditionally difficult, highly repetitive sequences that would completely jam chemical synthesizers. While writing data quickly is half the challenge, a functional enterprise-grade hard drive must also be able to reliably rewrite, edit, and read information on demand. Editing specific isolated files stored within a massive microscopic pool of billions of DNA data strands is mechanically complex. To solve this critical access issue, researchers are deeply integrating CRISPR-Cas systems into the hardware to act as a highly programmable, precise molecular cursor. In advanced conceptual systems like DNA mutational overriding storage, or DMOS, massive amounts of digital data are encoded into organized blank tapes of synthetic DNA registers. When a specific digital bit within a file needs to be updated or changed from a 0 to a 1, a highly programmed CRISPR complex, often paired with a deactivated dead Cas9 protein and an ApoBEC3A base editing enzyme, is deployed into the fluid reservoir. The CRISPR molecule acts as a highly efficient biological search engine. It physically scans the immense floating DNA archive until its attached guide RNA perfectly matches the exact target sequence, effectively locating the precise address of the specific data register that requires modification. Once firmly attached to the correct molecular address, the associated base editing enzyme is activated. It mechanically alters the chemical structure of a single target nucleotide, mutating it to reflect the new data state, effectively rewriting the binary bit directly within the long molecular chain, without fracturing or destroying the surrounding genetic architecture. This orthogonal and modular base editing methodology allows for the massive, parallel rewriting of data across thousands of individual DNA registers simultaneously, significantly accelerating data modification speeds. To bring this incredible technology out of the specialized laboratory and into physical commercial server racks, these complex enzymatic writing and editing reactions are being integrated directly into solid-state hardware through the extensive use of digital microfluidics. Modern prototype systems, such as the highly integrated DNA disk platform, utilize a dense array of microelectrodes printed directly onto a computer chip to precisely move, mix, split, and merge microscopic droplets of fluid with extreme precision. These tiny droplets contain the highly engineered TdT enzymes, the growing DNA strands, and the necessary sequential building blocks. By rapidly altering the electrical field on the surface of the chip, a process known as electrowetting, the hardware physically manipulates the biological droplets, allowing for fully automated end-to-end data storage and synthesis without any moving mechanical pumps or valves. To prevent long-term data degradation and physical clutter on the chip surface, the completely synthesized DNA is encapsulated in thermoresponsive agarose directly within the hardware, forming a stable, solid matrix. To read the data back into the standard computer system for the user, the specific DNA strands must be retrieved, isolated, and rapidly sequenced. The target sequence is first selectively amplified using polymerase chain reactions, utilizing specific primer sequences to create millions of identical copies of the target file while leaving the rest of the archive untouched. The amplified DNA is then routed directly to a highly integrated sequencing module, often utilizing advanced nanopore sequencing technology or rapid pyrosequencing. In nanopore systems, as the engineered DNA strand is physically pulled through a microscopic engineered pore in a synthetic membrane by an applied electrical current, highly sensitive sensors detect the minute disruptions in the electrical field caused by the distinct physical shape and size of each passing nucleotide. This sequencer continuously converts the physical topology of the molecular chain back into a continuous, high-speed stream of binary electrical data. However, because biological synthesis and sequencing are not perfectly flawless, the raw data stream often contains minute errors, such as missing bases or incorrect additions. To combat this and ensure absolute data integrity, the system relies on highly advanced data forensics and algorithmic error correction, utilizing complex mathematical models like Reed-Solomon codes and fountain codes. These algorithms, widely used in satellite communications and optical disks, embed calculated redundant information directly into the DNA sequence during the writing phase. When the DNA is read, the algorithms analyze the retrieved data droplets, identify any corrupted or missing sequences, and automatically reconstruct the original digital file with absolute fidelity. This seamless, highly orchestrated integration of enzymatic synthesis, CRISPR-based editing, digital microfluidics, and advanced algorithmic error correction represents the foundational, robust architecture for the next century of high-density information storage. Biobatteries and power generation, fueling electronics with metabolism. As consumer electronics, implantable medical diagnostics, and remote distributed sensor networks become increasingly miniaturized and ubiquitous, the physical constraints of traditional power sources have become a profound and limiting engineering bottleneck. Conventional lithium-ion batteries, alkaline cells, and standard capacitors are inherently bulky, rigid, and possess a finite, non-renewable energy capacity that strictly dictates the functional lifespan of the device. For critical devices that are physically embedded deep inside the human body, such as cardiac pacemakers, deep brain neural stimulators, and advanced automated drug delivery systems, replacing a depleted chemical battery requires highly invasive, risky, and expensive surgery. To overcome this severe physical limitation, engineers are bypassing traditional heavy metal chemical batteries entirely, looking instead to harness the highly efficient, continuous metabolic machinery of biology. This aggressive pursuit has led to the rapid advancement and commercialization of enzymatic biofuel cells, or EBFCs, an innovative class of advanced biobatteries that generate continuous electrical currents by metabolizing organic sugars found naturally and abundantly in the environment and the human body. Traditional industrial fuel cells generate electricity by constantly oxidizing highly reactive fuels like compressed hydrogen gas or liquid methanol over precious rare metal catalysts such as solid platinum or ruthenium. Enzymatic biofuel cells operate on the exact same fundamental thermodynamic principles of electron transfer, but they completely replace the rare, rigid, and expensive metals with highly specialized engineered biological enzymes. This biological substitution allows the miniature battery to operate efficiently at normal physiological temperatures at a near neutral pH, and critically, it allows the battery to run continuously on complex, naturally abundant organic fuels like glucose found constantly circulating in the human bloodstream, or lactate found in human sweat. The physical-mechanical architecture of an enzymatic biofuel cell consists of two highly specialized electrically isolated electrodes, the bioanode and the biocathode, which are separated by an electrolyte fluid that allows for ion exchange. In implantable medical applications or wearable patches, this necessary fluid is simply the user's own bloodstream, interstitial fluid, or sweat. At the bioanode, specific highly active oxidoreductase enzymes, most commonly glucose oxidase or glucose dehydrogenase, are densely immobilized onto a highly conductive hardware substrate. As the physiological fluid continuously washes over the active surface of the bioanode, the immobilized enzyme captures passing glucose molecules and instantly catalyzes a rapid, highly controlled oxidation reaction. During this precise mechanical action, the enzyme physically breaks the chemical bonds of the sugar molecule, rapidly stripping away high-energy electrons. Extracting these liberated electrons from the core of the biological enzyme and routing them efficiently into the rigid electronic hardware is a major, highly complex engineering challenge. Enzymes are massive, complexly folded, highly dense protein structures, and their active sites, where the actual chemical reaction and electron stripping take place, are often buried deep within a thick, electrically insulating shell of amino acids. To bridge this physical, highly resistive gap, engineers utilize two primary methods of electron transfer: mediated electron transfer, MET, and direct electron transfer, DET. In mediated systems, highly mobile, easily reducible molecular shuttles, known as redox mediators, are introduced into the battery's chemical architecture. These tiny molecules physically diffuse and dive deep into the enzyme structure, grab the stripped electron directly from the active site, and ferry it back to the surface of the electrode, facilitating the steady flow of electrical current. While functionally effective for initial prototypes, mediators can diffuse too far and permanently escape the battery environment over time, leading to a steady, unavoidable degradation of total power output and severely limiting the long-term multi-year stability of the medical device. Consequently, cutting-edge biobatteries are aggressively moving toward direct electron transfer mechanisms to ensure permanent stability. By using heavily engineered, highly conductive three-dimensional nanostructures, such as highly aligned carbon nanotubes, highly porous gold nanoparticles, complex metal organic frameworks, or conducting polymers like polyaniline, the hardware is built to physically pierce or intimately wrap around the outer insulating shell of the enzyme. This extremely close physical proximity establishes a direct physical nanowire to the active site, allowing electrons to flow instantaneously and continuously from the metabolizing sugar directly into the device's circuitry, without the need for any chemical shuttles. Once the electrons successfully enter the conductive circuit, they travel rapidly through the electronic device, actively powering the pacemaker's logic board, the smartwatch's complex sensor array, or the wearable patch's data transmission antenna, before arriving at the opposing electrode, the biocathode. Here, a second set of highly specific enzymes, typically lacase or bilirubin oxidase, is densely immobilized. These specific biocatalysts take the spent, low-energy electrons from the circuit and use them to catalyze the rapid reduction of ambient oxygen molecules, dissolved naturally in the body fluid or the surrounding air. The enzymes mechanically combine the oxygen with free hydrogen ions to produce pure water as the only resulting byproduct of the entire sequence. The entire electrical circuit is completely closed, entirely self-sustaining, and runs continuously without any external input as long as the user's body supplies a steady, natural flow of glucose and oxygen. A significant operational limitation of early prototype biofuel cells was their complete inability to handle the highly fluctuating, intense power demands of modern digital hardware. While a standard enzymatic biobattery excels at producing a steady, continuous trickle of low-level electrical current, complex medical devices like neural stimulators, advanced diagnostics, or wireless Bluetooth transmitters require sudden, intense bursts of power to function momentarily and transmit a data packet. Traditional chemical batteries face this exact same physical limitation, which is why commercial electronics inevitably pair standard batteries with supercapacitors, which are specialized hardware components that rapidly store electrical charge and release it instantly on demand in a massive pulse. To adapt enzymatic fuel cells for highly practical, high-draw consumer electronics and advanced medical implants, engineers have successfully merged the continuous biobattery and the rapid supercapacitor into a single, highly compact, monolithic physical structure. By securely housing the glucose-oxidizing enzymes within a specialized, highly conductive redox polymer matrix, such as precisely formulated polyethyleneamine, the polymer itself acts as a massive charge storage reservoir, effectively functioning as the supercapacitor. The enzymes constantly metabolize sugar at their own steady rate, filling the dense polymer matrix with electrical charge over time. When the medical implant suddenly needs to send a data packet or fire an intense electrical pulse into cardiac tissue, the polymer instantly dumps the massively stored pool of electrons into the circuit, providing the necessary high-energy burst without interrupting or crashing the underlying continuous enzymatic metabolism. The ultimate highly scalable realization of this power technology is the seamless integration of these biobatteries directly onto standard silicon computer chips or ultra-thin flexible substrates. Advanced fabrication techniques now allow the precise microscopic deposition of enzymatic layers onto microchip architectures using the exact same photolithographic and printing processes used to manufacture standard consumer computer processors. This high-throughput capability has resulted in the development of ultra-thin, highly flexible paper-based fuel cells that can be easily mass-produced at an incredibly low cost. Companies are currently developing miniature paper-based bioenzymatic fuel cells that utilize conductive carbon paper and heavily stabilized enzymes to power active sensor tags, global logistics trackers, and highly distributed Internet of Things devices. The physical mechanics of these specific paper-based devices rely heavily on highly engineered capillary flow within the substrate. Rather than utilizing moving mechanical pumps to move fluid across the electrodes, the microscopic channels within the paper or moisture management fabrics rapidly wick fluid across the battery architecture, ensuring a constant, high-speed delivery of reactants and rapid removal of byproducts. These devices are instantly activated by applying a single small drop of liquid, immediately initiating the enzymatic biocatalysis. Once activated, they generate highly impressive power outputs, reaching several milliwatts per square centimeter, easily providing enough continuous power to run microprocessors and wireless transmitters. By successfully harnessing the highly efficient, room-temperature metabolic pathways refined by millions of years of biology, the technology sector is pioneering a massive era of autonomous, self-powered devices that are fundamentally integrated into the physiological mechanics of the user and the surrounding environment. Precision manufacturing, the biocatalytic foundry. The relentless, exponential advancement of consumer electronics, artificial intelligence processors, and high-performance computing, driven by the exacting principles of Moore's law, strictly demands the continuous and highly aggressive miniaturization of transistors, memory cells, and microchips. Today, billions of incredibly microscopic components are printed onto a single, highly polished silicon wafer, with individual features measuring only a few nanometers across. At this extreme atomic nanoscale, the absolute physical margin for manufacturing error is essentially zero. To successfully stack dozens of intricately interconnected circuit layers on top of one another without causing a short circuit, the entire surface of the semiconductor wafer must be repeatedly planarized or flattened to a state of near-perfect atomic smoothness between each and every photolithographic step. This critical, highly sensitive manufacturing process is achieved through an intense mechanical operation called chemical mechanical planarization, or CMP. In a highly traditional CMP process, the semiconductor wafer is pressed face down with significant mechanical force against a rapidly rotating, heavily grooved polyurethane polishing pad. A highly specialized, highly engineered fluid known as a slurry is continuously pumped onto the rotating pad. This slurry contains highly aggressive, corrosive chemical oxidizing agents and millions of microscopic, incredibly hard abrasive nanoparticles such as silica, ceria, or alumina. The chemical agents rapidly react with the surface of the wafer, rapidly oxidizing the top layer of material to make it structurally softer, while the hard nanoparticles physically grind and rip the softened material away. However, as the global semiconductor industry rapidly shifts away from traditional silicon toward next-generation, incredibly durable materials designed for high-power electronics and rapid switching, traditional CMP encounters severe, insurmountable mechanical limitations. Modern electric vehicles, advanced military radar systems, high-frequency 5G transmitters, and high-efficiency power converters require semiconductors capable of handling massive voltages, extreme frequencies, and extreme thermal loads without melting or degrading. To meet these rigorous high-stress demands, the industry relies entirely on wide bandgap compound materials, primarily silicon carbide and gallium nitride. The defining physical feature of these wide bandgap materials is their incredibly robust, tightly bound atomic lattice and incredibly high electron mobility. Silicon carbide, for example, is highly chemically inert and possesses an extreme physical hardness approaching that of pure diamond, making it exceptionally resistant to traditional processing and polishing methods. When traditional CMP slurries are applied to silicon carbide or gallium nitride wafers, the standard chemical oxidizers completely fail to penetrate or alter the surface efficiently. Consequently, the entire manufacturing process must rely almost entirely on immense raw mechanical pressure and incredibly hard diamond abrasives to physically grind the inert material down. This brute force approach results in painfully slow material removal rates, often taking dozens or even hundreds of hours to polish a single wafer, thereby drastically increasing manufacturing costs and bottlenecking global supply chains. Worse, the extreme mechanical force drives the abrasive particles deep into the atomic lattice, creating microscopic scratch defects, deep subsurface fractures, and massive stress zones that can completely ruin the electronic properties and structural integrity of the final microchip. To completely solve this profound materials science bottleneck, advanced hardware fabricators have begun introducing highly specialized industrial enzymes directly into the abrasive polishing fluid, initiating a revolutionary manufacturing process known as biocatalytic chemical mechanical planarization, or bio-CMP. By integrating specific, highly engineered oxidoreductase enzymes, such as chloroperoxidase or specialized peroxidases directly into the abrasive polishing fluid, engineers can fundamentally alter the surface chemistry of the ultra-hard wafer without resorting to brute physical force. The elegancy of biocatalytic polishing lies entirely in the enzyme's ability to drive highly specific, exceptionally aggressive chemical reactions directly at the solid-liquid interface of the rapidly spinning wafer. When the biocatalytic slurry flows over the silicon carbide, the enzymes facilitate a rapid, highly localized atomic-level oxidation reaction. These enzymatic systems are often paired directly with secondary enzymes like glucose oxidase to continuously generate necessary, highly reactive reactants such as hydrogen peroxide, perfectly in situ during the exact moment of polishing. The enzymes constantly aggressively target the silicon and carbon bonds exclusively on the absolute top atomic layer of the wafer. This precise, continuous enzymatic reaction systematically converts the ultra-hard, impenetrable crystalline surface into a microscopically thin, vastly softer oxide layer. Because the enzyme performs the heavy lifting of breaking the surface bonds chemically, the massive CMP polishing machine requires significantly less mechanical pressure to achieve planarization. The polishing pad and much softer, significantly less destructive abrasive nanoparticles can now gently sweep away the oxidized layer without fracturing, scratching, or stressing the pristine, unreacted atomic lattice situated directly beneath it. This deep enzymatic integration not only drastically accelerates the absolute polishing and material removal rate of advanced wide bandgap semiconductors, reaching enhancement factors exponentially higher than traditional methods, but dramatically reduces the frequency of microscopic scratches and subsurface defects, ensuring maximum yield and flawless performance for the fabrication plant. Similar advanced enzymatic processes, utilizing plasma-assisted polishing and precise electrochemical machining, are also being aggressively developed to rapidly polish diamond substrates, the absolute hardest material on Earth, for use as ultra-efficient heat sinks in advanced electronics. The integration of advanced biological tools extends far beyond physical polishing and deep into the highly critical realm of semiconductor tweening and photolithography. Throughout the incredibly intricate fabrication of a microchip, the entire silicon wafer is repeatedly coated with a highly specific, light-sensitive polymer known as photoresist. A highly complex, nanoscale circuit pattern is projected onto the resist using extreme ultraviolet light, and the exposed areas are chemically etched away to form the intricate microscopic wires and transistors. Once the circuitry is permanently carved into the silicon or metal layers, the remaining heavily baked-on, heavily cross-linked organic photoresist mask must be completely stripped from the wafer to proceed to the next layer. Even a single microscopic speck of leftover polymer residue or debris can cause a catastrophic short circuit or physical blockage in the final device, ruining the entire chip. Traditionally, removing highly cross-linked negative photoresist requires completely submerging the delicate wafer in highly volatile, highly aggressive organic solvents like acetone, N-methyl-2-pyrrolidone, or dimethyl sulfoxide. Alternatively, manufacturers utilize highly corrosive acidic mixtures, such as sulfuric peroxide, or deploy incredibly high-energy plasma ashing machines to literally burn the organic polymer away from the surface. These highly aggressive cleaning methods pose a severe, constant risk of physically damaging, melting, or corroding the incredibly delicate nanometer-scale metal wires, such as tungsten or copper, freshly printed on the chip. Furthermore, highly concentrated alkaline media used in some cleaning steps can actively etch and destroy the crystalline silicon itself. To entirely mitigate this massive risk and ensure absolutely pristine surface preparation without any collateral damage, semiconductor foundries are rapidly developing and deploying advanced, highly targeted enzymatic cleaning formulations. By synthesizing targeted, highly complex cocktails of industrial enzymes, specifically utilizing heavily engineered proteases, lipases, and cellulases, the cleaning fluid can be chemically programmed to seek out and dismantle the specific molecular bonds of the organic photoresist and post-etch residues. When the processed wafer is fully immersed in the enzymatic bath, the enzymes rapidly latch on to the hardened, cross-linked polymer chains of the photoresist. Proteases and lipases methodically and rapidly cleave the complex molecular structures into much smaller, highly soluble fragments that can be easily rinsed away with pure deionized water. This biological dismantling process operates highly effectively at low room temperatures and near neutral pH levels, ensuring that the aggressive cleaning action is completely and strictly restricted to the unwanted organic residue. The underlying pristine silicon crystal, the incredibly delicate metal interconnects, and the highly sensitive dielectric materials remain entirely untouched, uncorroded, and structurally perfect because the enzymes are structurally incapable of reacting with inorganic metals or oxides. Furthermore, researchers are actively exploring highly advanced enzymatic etching techniques, utilizing highly specific enzymes like horseradish peroxidase to generate highly controlled free radicals that can precisely etch semiconductor nanoparticles, quantum dots, and gold nanorods to perfectly tune their optical and electronic properties for advanced sensors and photoelectrochemical devices. As semiconductor features relentlessly shrink to dimensions measured in mere individual atoms, this level of absolute chemical specificity and completely damage-free processing is no longer just a manufacturing advantage. It has become an absolute mechanical necessity for the continuation of Moore's law and the future of hardware fabrication. The deep structural integration of highly engineered industrial enzymes into modern technology represents a profound, necessary, and absolute expansion of the hardware toolkit. For decades, the global technology industry has relied exclusively on the brute manipulation of physics, extreme heat, and incredibly harsh inorganic chemistry to build, power, and expand the digital world. However, as physical limits are aggressively reached in miniaturization, power density, and data storage, the rapid shift toward biocatalytic integration proves definitively that the highly refined microscopic machinery of the biological world can be effectively harnessed, structurally controlled, and directly embedded into consumer electronics, massive power systems, and advanced industrial fabrication pipelines. From the wearable biosensors and smartwatches that successfully translate the highly chaotic chemical language of human physiology into pristine binary data using specialized enzyme-gated transistors and advanced biological logic gates, to the massive deployment of complex polymerase enzymes and highly programmable CRISPR-Cas systems as highly accurate rapid molecular writing and editing tools for the massive DNA data archives of the future, biology is actively providing the specific atomic-level mechanical solutions to some of technology's most intractable physical limits. Enzymatic biofuel cells, utilizing complex direct electron transfer and highly conductive nanostructures, are actively redefining the fundamental physical parameters of power generation. They prove that electrical energy does not exclusively need to be stored in rigid heavy metal cells, but can be continuously harvested and metabolized from the ambient environment and the human bloodstream to permanently power life-saving medical implants and ubiquitous sensor networks. Furthermore, within the hyper-controlled, incredibly demanding environments of global semiconductor foundries, the delicate atomic-level touch of biological enzymes is proving far superior to raw mechanical force, diamond abrasives, and aggressive acids. This enables the flawless, extremely rapid, defect-free fabrication and precision cleaning of the hardest, most advanced wide-bandgap microchips in the world, ensuring the continued exponential growth of computing power. This incredible synthesis of wetware and hardware, often conceptualized as the foundation for the Internet of Bio-Nano Things, or IBONT, is fundamentally altering the trajectory of digital innovation. By seamlessly bridging the biological and cyber domains, and utilizing the precise atomic-level manipulation natively programmed into biological catalysts, the next generation of technology will operate with a level of sophistication, efficiency, and deep integration previously thought physically impossible. The high-performance machines, computers, and diagnostic devices of tomorrow will not just be manufactured through traditional industrial means, they will be biologically catalyzed.